video, we would like to introduce our final project proposal, context-aware reference, refinement for image insertion via diffusion transformers, which aim to improve contextual consistency in insert anything. Our presentation will begin with an introduction to the image insertion task, followed by a survey of related work, including task-specific insertion methods, reference-based generation, and unified image editing frameworks. We will then discuss our chosen baseline insert anything and analyze its main weakness in contextual consistency. After that, we will introduce our robust methods, evaluation plan, datasets, experimental settings, system demos design, expected difficulties, and conclusion. So image insertion aim to seamlessly place a reference object or person into a target scene while making the final image look natural and realistic. This task has many practical applications such as virtual trial, cinematic editing, and personalized content generation. However, image insertion is still challenging. First, the model should support unified editing across diverse objects and scenarios with flexible user control through front or masks. Second, the 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 inserted object must be contextually consistent with the target scene. Finally, it should interact realistically with the surrounding environment, including lighting, colors, shadows, and overall image harmonization. You can see some visual example of this task on screen right here. And I mentioned earlier, image insertion still has several challenges, including flexible editing, contextual consistency, and realistic interaction with the target scene. Therefore, our research question is, how can we develop a method that addresses these challenges and produces more natural image insertion results? Following is the result of our survey on this topic. First, we explore methods in the category of task-specific image insertion. One example is Anidor zero-shot object-level image customization. Anidor introduces a zero-shot object insertion framework that can place a reference object into a new scene without object-specific training. It preserves object identity using Dino version 2 features, maintain fine detail through high-frequency maps. The identity and detail features are injected into stable diffusion to generate realistic and controllable object insertion results. This framework supports shape and location control for user-provided maps. For the strength of these methods, Anidor shows strong appearance preservation and good image harmonization. The inserted objects can blend naturally with the target scene while still maintaining their original visual identity. However, the method also has several limitations. First, it mainly relies on mask-based editing, which limits editing flexibility and versatility. Second, the framework is specifically designed for object insertion tasks, making it less generalizable to broader image editing scenarios. Finally, it still struggles with complex contextual adaptation and reserving very fine details such as logos or intricate textures. Next is Trimboot. Trimboot is a preference-based image generation method designed for subject-driven generation. Its main idea to personalize a text-to-image diffusion model using only a few reference images using around 3 to 5 images. The key innovation is that Trimboot learns to bind a unique identified token to a specific subject. After fine-tuning, this token can be used in text prompt to generate the same subject in new scenes, poses, styles, and lighting conditions. The main idea is to teach the model to associate the subject with a unique identifier. For example, here on screen is a token AV dog represent a specific object, while the light dog help the model use its existence knowledge of that category. To reserve both subject identity and generation diversity, Trimble introduced a class-specific prior reservation laws. This helped the model avoid forgetting the general concept of the subject class, such as a dog or person, while learning the specific subject instance. Um, of course, it also has several advantages. It produces images with strong contextual coherence and realistic interaction between the subject and the generated scene. It also preserves the identity and appearance of personalized object very well, making the generated subject remain recognizable across different prompts. However, Dream Boot also has some drawbacks. It does not offer direct spatial or mass space control, so precise placement is difficult. It also requires fine tuning for each new subject, which makes the process less efficient and harder to scale. Moreover, subject features may become entangled with the training context.
Next, we move to unified image editing frameworks. The representative method in this category is AnyEdit, which aims to support high-quality instruction-based image editing across many different editing tasks. The main idea of AnyEdit is to overcome the limitations of previous editing datasets, which are often limited in task diversity and data quality. To address this, AnyEdit builds a large-scale dataset with diverse editing types, covering local edits, global edits, camera movement, implicit reasoning, and visual guided editing. In addition, AnyEdit introduces an adaptive data collection pipeline and quality filtering strategy to ensure that the editing pairs are both semantically correct and visually realistic. Beyond this dataset, the author further developed NESHD, a task-aware diffusion model that can handle different editing tasks within one unified framework. AnyEdit has several key advantages. It can produce a wide range of editing instructions within one unified framework. It accepted different types of visual guidance, including depth, sketch, segmentation, and reference images. At the same time, NED still be able to keep the edited image visually consistent, making it more effective for complex and uh, and detailed editing scenarios. However, any edit still has some weaknesses. Because of its based on diffusion models, the editing process requires iterative inference uh, and can be time consuming. Its data construction and training pipeline are also complicated, requiring a large amount of carefully curated editing data. And in addition, when handling complex reasoning edits, the model may still introduce artifacts or train more parts of the image than intended. Finally, we move to methods related to in-context image insertion. For this category, we choose insert anything as the representative work, and this also our chosen byline. The main contribution of this framework is to introduce a unified image insertion model that can insert any object into any scene using a single architecture. The pipeline of this method can be divided into four main stages. First, the model takes three inputs: a reference image, a source image, and a control prompt, which can be either a mask or a text instruction. And the reference object is separated from its background using segmentation tools such as grounding dino or SAM. Next, the inputs are arranged into a multiple panel former called a polytype. For mask-based editing, the model uses a diptych with a reference object and mask source image. For text for text-based editing, it's use a chief text with the reference object, source image, and an empty target regions. Then the model extracts both visual and semantic information. A thousand VAE encoder preserve image details, while clip or DeFi provides semantic guidance depending on whether the prompt is image-based or text-based. The core model is a diffusion transformer or DIT, which use multimodal attention to combine image and text information during denoising. Finally, a VAE decoder reconstructs the final image. During inference, an adaptive cross strategy helps preserve details for small inserted objects. Insert anything offers several notable advantages. First, it's generalized across different object categories, such as human or object and insertion scenarios, without requiring separate task-specific models. Next, it supports both mask-guided and text-guided insertion. It allows users to control not only where the object is inserted, but also how it should appear in the target scene. Finally, insert anything is strong at preserving identity, texture, and appearance details. It also improves the generation quality of challenging regions such as faces, fine textures, and small objects. Due to the advantages, we should insert anything as our baseline. However, the generated results may still show some contextual inconsistencies in complex scene.
Okay, despite the advantage, insert anything still has some limitations. As shown here, image, text, and latent feature are directly injected into the DAT blocks, meaning model mainly rely on the implicit feature fusion inside the transformer. Although DAT is powerful, this design does not explicitly involve contextual alignment between the insert object and the target scene. As a result, the framework research object identify well, but contextual can still be inconsistency, such as mismatched lighting, scale, or scene semantic. As I said, insert anything mainly rely on the implicit feature fusion inside the DIT blocks. Because of that, even though it research object identify well, but the contextual compatibility of the generated result can still is inconsistent. As the result we show on the screen, you can see that the framework misunderstand the scene content and place the reference object in incorrect pose. You can see the pose of the person in this image. Another weakness of this framework is that the foreground and background sometimes don't blend similarly, especially in terms of the color tone, lighting, and the overall atmosphere of the scene. As we can see in this example, the insert object still retain the color and lighting from the reference image. The different color tone is clearly visible, making the insert object look unnatural against the background. Because of these shortcomings, we are motivated to introduce an explicit context-aware feature model before diffusion generation. And this is the overall proposed method. The key idea of our method is add to the explicit context-aware feature module before DAT generation. in the original insert anything framework, and the reference feature and the scene feature are directly fused inside the DAT block. In our method, we first pass the reference and the scene feature through the harmonization module. Then the feature are sent into the DIT for final image generation. Inside the module, the feature first go to the crowd attention for semantic alignment, followed by feature modularization for contextual adaptation, and finally lightweight refinement stage before being passed into the DIT generator. And for the evaluation, we use for evaluation metric first dino score is used to measure identify preservation, and the second LPIPS measure the perceptual consistency, focus on visual similarity from the human perception perspective, and third FOS score measure the foreground and background compatibility, and finally FID is used to evaluate the overall system and the quality of the generated image. And for this start, we use three datasets for insert from insert anything remote, and VO, VTO, and HG for training and evaluation. And in this slide, the expected improvement of our method include better contextual between the insert object and the target scene. At the same time, the framework AM2 refers the reference identified while improving overall visual harmony. And we also expect improved lighting and apparent adaptation, allowing the insert object blend more natural into the different environment. And finally, the method is designed to produce more realistic interaction between the insert object and the surrounding scene context. And for the experiment setting, we use insert anything as the baseline and add our robot method module on top of it. With this design, we expect the robot module to improve the contextual real-time while still maintaining the strong identify fidelity. And we also repair a demo interface, and literally our current demo interface. In this example, the original image contains a basketball playing wearing a purple shirt, and we want to replace it with the other jersey. We first specify the target region using the mask, and where the two mask region correspond the clothing area we want to modify. And after clicking generation button, the model produces a new image in which the player has been successfully replaced, while reversing overall identify and pose of the player. And there when we do this project, we also have some several challenges in the work. First, the training stability is another challenge due to the complexity of diffusion-based generation and feature harmonization. And the second, balancing contextual harmony and identify preservation can be difficult. Since improving scene compatibility may sometimes weaken the original appearance of the reference object, and the GPU limitation may also restrict training scale, but size and overall experiment efficiency. And finally, we also expect difficult in contextual generation, especially when handling diverse scene and insertion scenario. And to the conclude, we propose a lightweight scene-aware uh, harmonization module to improve contextual compatibility in the diffusion-based image insertion. And the goal is to make inserted the object blend more natural with the target scene while preserve their original identify and appearance. Thanks for your listening.